Yeah, I'm really hoping it will be rewatchable, because it's one of those topics, isn't it? It's so tricky, and it'd be really nice to have like an archived video or a session where if someone's struggling, we can say, I've got exactly the thing for you. Here it is. And saving engineers tend to like solving problems once. You solve a problem once, and then we have code for this or a video for this, and then we can move on and think about other things.
Yeah, that's true.
I had an interesting one at work recently where one of the other engineers came up to me and said, how do I do heat transfer coefficient in CFX or Fluent? And I said, here's a video for you. I sent him a video.
Was it the video from you? Or?
Oh, it was my own video.
That's good.
Oh, that's really good. Yeah.
Do you sometimes also go back to your own videos to recheck things?
I do sometimes, but you know what? When you look back at your own videos and you see yourself a few years ago and you think, I was so young and my audio quality was so bad.
That's true.
Yeah. This is a discussion I often have with my brother, that as you mature as an engineer or a scientist in any regard, you get better at what you're doing. And there's always a temptation when you look back at your old work and you think, oh, I could go back and redo it because I'm so much better now. My presentation's better, my technical ability's better. I can go back and redo my old work. But that's a trap, because you can always go back and redo your old work and you get better again, and then you'd have to go back and do it all over again. And you almost have to come to peace with your old work being what it is.
Yeah, that's true. I've seen bigger YouTubers do that. Every 4 or 5 months, they rename the title a bit, but redo the same content. But if you don't have too many videos, you would actually see it. There's like 10 Y+ videos.
I know. I've been redoing it every year. But this one, I thought it's been probably 3 or 4 years since I've filmed my first video. And after talking with lots of people and working out where people were having difficulties, I've sort of brought everything together into that talk and made it more focused on what you should actually do rather than what's the CFD code's doing. So,
yeah. But, very cool. All right, Aidan, we can kick things off now.
Yeah, I'll kick things off. And if anyone else joins, they can always, or they can catch up on the recording later. Okay. So this workshop is going to pick up from where we left off in the talk from the previous session, where we're actually going to be using estimations to think about the layers that we grow when we're generating a mesh. And this one's going to be a bit more practical. So I hope you guys are going to like this. And just the background for this is that in most CFD calculations that you're going to do, you're going to have walls, whether that be on the surface of an aerofoil or the boundaries of your domain. If you have an internal flow or something complex, you're always going to have walls. And for those important surfaces where you really need to know the forces and the heat fluxes and the mass fluxes to get the correct answer, inflation layers or prism layers or boundary layers, as some people call them, need to be grown from the wall, which may look something like this. And it doesn't really matter whether you're using an unstructured mesh generator or a structured mesh generator or something block structured. This kind of structure of having thin cells close to the wall and then growing them away is always going to be there when you're doing RANS calculations. And so what we're going to do in this workshop is we're not just going to be looking at that first layer, we're going to be looking at all the layers, and we're going to be looking at how we can estimate what sort of layers we should be generating. And it's going to be really practical and showing you the calculations that you should do, not on the buttons that you click in the mesh generator, because of course there are many different mesh generators and I don't know which one you're using. You may be using your own one or something which we've never used before, but I'm actually going to be showing you the parameters that you'd want to put into your mesh generator in this workshop, and you're going to have a go as well. So how we're going to do this is this one's going to be a bit more practical. Rather than me talking, I'm going to get you to do some of the calculations as well. And what I've done is I've put together an inflation layer calculator on my website, which You can get it on, you can load it up on your laptop, on your computer now, or on your mobile as well. And this was the reason I decided to put this calculator on a website rather than just having it as some MATLAB code or some Python code. I wanted it on a web page so that wherever you are, if you're at work or if you're on your home computer and you think, oh, I've got to do a mesh, I need to work out what sort of layers should I be generating, you can quickly pull this calculator up. It's really easy, and it works on your phone and on your computer. So you can either follow this link to fluidmechanics101.com, or you can actually find it really easily on just with a quick Google search. So if I go to Google and just type in fluid mechanics 101 into Google, and what comes up first is you have the YouTube links, but you can also go to my website. That's the one you want, fluidmechanics101.com. And then in the top, you'll see it's got home, I've got some courses, lectures, and it's calculators that you want. If you click on calculators at the top, and what I have on this website are just a range of very simple calculators, which you can quickly grab up on a web page or grab up on your phone if you want. And the calculator we want is the inflation layer calculator, which is right at the top here. And before I jump into the calculator and how it works, many people will want to know what's actually going on behind the scenes. What's this calculator doing? And right at the bottom of the page, there's a PDF document here, which you can open up again on your phone or on the web browser. And what the PDF document does is it actually has all the equations in here that the calculators all use. And the reason I've put that in there is firstly for your reference and understanding. You may want to know what's the calculator actually doing, but also for a security reason as well. And that is principally that, of course, what I'm showing you here is how to use an online calculator to do an engineering calculation. And it's really important to remember that whether you choose to use my calculator or you type into Google and find some other calculator, you don't know what the calculator is doing really. And if you're in a company or in certain industries, using an online calculator to do an engineering calculation isn't very appropriate, and often that won't be signed off as an appropriate calculation, and you'll actually need to do the calculation yourself so that someone can check it and verify that it's okay. And that's why I've included the document here with the equations. So if you want to make something similar yourself, or your line manager or your boss queries what you've done, you can just take these equations and type them straight into MATLAB or Python or whatever code you're using as well and recreate it. So that's obviously going to be a lot more reliable than using a calculator on the internet, because I may have made a mistake or the calculator may not be doing what it says it's doing. So that's for your own benefit. You can always read up, and the calculator fully explained there. But what does this calculator actually do? What does it do? Well, basically what it does is, the first thing that it does is it has that empirical correlation that we went through in the first workshop coded into it. And so we can use it to estimate, firstly, what the height of the first cell should be to give you the target Y+ that you want. But then the other thing that this calculator does, which is so important, is it's also going to calculate the growth ratio. So what geometric growth ratio should you use for the layers so that they can get bigger as you go away from the surface? And how many layers should you use? Where are the layers going to stop? And just to give you an indication of what the calculator does and how it works, it's already got some default values grayed in here, just as an example. And you can type in your values and click calculate. And what the calculator is going to do is it's going to tell you what the height of your first layer should be. So if you say, I want a target Y+ of 1, fill in your parameters, it will tell you the height of your first layer, what the height of the final layer will be. That will be important for us later. It will also estimate the boundary layer thickness and what the growth ratio of the layers should be normal to the wall. So this is what the calculator, yep.
Could you quickly explain what the inflation layer means? We had a question.
Yes. Yes, of course. Sorry, I'm not looking at the chat. So what happens when you generate a mesh is you start from the surface of your object. So if you have an aerofoil or a car, for example, the first thing the mesh generator will do is divide that surface into squares and triangles, and that's the surface. And then what the mesh generator will do is it will project that surface off the surface to create that first layer of cells. And that's the first layer, and that's the first layer thickness for the Y plus calculation. But then it will then grow that layer again, and it will continue to project the surface mesh off the surface to generate layers of cells on top of each other, which are normal to the wall. And that projection process is really good because we know that normal to the wall, we have a characteristic velocity profile. And so we want those layers to be projected off the wall. And they're called inflation layers because much like a balloon, they inflate and they get bigger as you grow away. And they're getting bigger because remember, the profile gets less steep as we go further away from the wall. So we can have bigger layers and a less steep velocity profile with linear sections between it. So these are the inflation layers, and this is a slice through the mesh. And yeah, please let me know if there are any other questions because I can't see the chat at the moment. But let's just flick back to the slides. So hopefully you've managed to find the website and find the calculator as well. If you're having trouble, just again, let us know in the chat and we can pause and go back to that. What I want to do now is really to show you how to use it. And that's going to be the main emphasis of this workshop. And once I've shown you how to use it, I'm going to get you to give it a go as well for some common flow problems so you get the idea. So this is the example that I'm going to do. I'm going to show you how to use it, and then you're going to go away and I'm going to do some extra examples. So let's say we have a wing. We have a wing of a plane or a blade of a wind turbine or an aerofoil, which is 1.2 meters in length. That's the length of the aerofoil. And we've got air coming in at 5 meters per second approaching the aerofoil. And as a CFD engineer, you've been tasked with create a mesh for this aerofoil and tell me what the lift coefficient, the drag coefficient, and what the forces on it are. So you're going to need to create a mesh, and your mesh generator will wrap inflation layers around the surface of the aerofoil. But you're going to need to tell it how thin is that first layer for the Y plus you want, how many layers do you want, and how fast should they grow away from the surface. So we've got all the parameters we need. We've got the size of the body, the speed of the airflow, and air's dynamic viscosity and its density. So let me put these, I'll put these side by side. So in the calculator, the first thing we need is the velocity, and I've got a velocity of 5 meters per second, the length scale or characteristic length of the object. So for an aerofoil, it's just going to be the length. The dynamic viscosity, that's 1.81 times 10 to the minus 5. Density of 1.225. And then target Y plus. What Y plus do I want? From the previous talk, you might remember that for aerofoils, when the flow is attached, we could have quite a large Y plus, probably a 30. But if we want those really accurate simulations and we don't want reviewers to question our mesh, we want it to be really fine, we'll have a Y plus of 1. And how many layers do I want? This is something I haven't really spoken about yet, but usually layers somewhere between 10 and 30 are what's used in CFD. For this example, I'm going to go with 20. That's quite a lot of layers. I'm using a lot of layers, so I'm going to get quite an accurate result. Let's click calculate. Please fill in all fields. So I've missed something, the length scale. 2, calculate, and you can see that the numbers appear right away in the box below. The calculator tells me the first layer height is 1.26 times 10 to the minus 4 meters. So that's 0.1 millimeter. So a really, really thin cell on the surface of that aerofoil. And then it's telling me that the boundary layer thickness is going to be about 9 millimeters. You can see again, it thinks the boundary layer is going to be about 9 millimeters. It's quite thin. And the maximum growth ratio. So this is how much bigger does each layer get compared to the layer before it, is 1.12. And Of course, you could use 1.12. If you used a smaller value, you'd have thinner layers, which would take longer to grow. And if you had a larger value, those layers would get thicker faster. I'm going to talk a bit more about that later. But those parameters, definitely the first layer height and the max growth ratio, you could put those straight into your mesh generator and it would generate some layers and generate a mesh. So for this second example, which I want you to have a go at, we've got something very similar. We've got water approaching a circular cylinder with a diameter of 0.5 meter. And of course, the dynamic viscosity and density of water are different to air. And again, this is flow over a cylinder. We're probably going to get a Kalman vortex street behind it, some unsteady flow. So we want a Y plus of 1. And this time, let's go with 15 layers instead. If I stop sharing and then give you guys, if I give you a minute or two just to give that a go, and then when you've got some parameters, someone just puts a thumbs up in the chat or something, or a yes when you've managed to use the calculator, I'll move on and go through the answers. All right, let's jump back in and do the answers. So if I've got a velocity of 1 meter per second, my length scale is, in this case, the diameter of the cylinder. It's 0.5 meters. The dynamic viscosity of water is quite a lot larger than air. The density is 1,000. Target Y plus of 1, and I only want 15 layers. And I can see that my first layer height is 5.5 times 10 to the minus 5. So this is a really, really thin mesh. And you can start to see why that when your layers are that small, this is why when you're aiming for that Y plus of 1, you often get loads and loads of cells in your mesh, and the cells are really, really small. This is why the calculations take quite a long time. You get an accurate solution, but it takes a long time to get there. And a growth ratio of 1.2. So you can see already that typically we're starting to see growth ratios in the range of maybe 1.1 to 1.3 are what most often are required. But what's actually happening here? How is the calculator calculating these numbers? I'm just going to take a small detour to talk about this. Well, what the calculator is actually doing is it's estimating the boundary layer thickness. It's estimating the boundary layer thickness, and then it's calculating the layers so that the total height of all the layers fits within the physical boundary layer. So that might take a few minutes for that to sink in. Remember, the boundary layer is the physical region of flow that's close to the wall, and the boundary layer thickness is typically defined with a delta 99. That's where the flow velocity has reached 99% of the free stream velocity. So all of the complex flow is going to be happening within the boundary layer where that velocity profile changes really steeply. And so the calculator works by trying to fit the boundary layer within the layers. And that's really good for us because layers, they're normal to the wall, so they're going to do a really good job of capturing those profiles. We haven't got any tetrahedra or triangles or polyhedra in here. The boundary layer, the difficult bit of the flow is all captured by the high quality inflation layers. And that's why it's estimating the boundary layer thickness, and it's adjusting the growth ratio so that the number of layers we specify will fit exactly within that boundary layer. That's what the calculator is doing. Now, for another example, this one's probably a bit more typical of something you might see in an internal flow scenario. We've got a few different dimensions here, and this is where we actually have to start thinking. This is air coming into a ducting system. The air is coming in at 2 meters per second, and the ducting system, it's got a length of 10 meters. It then goes over a step, got 15 meters, and then the outlet's 2 meters high. And again, we've got airflow. The dynamic viscosity is, again, lower than it was for water, and the density is much lower as well. But this time, because we've got airflow in a ducting system, you can imagine that the flow in that initial section of duct is probably going to be quite similar to the empirical data that was used to generate those universal flow profiles in the pipe flow or the channel flow. And so actually in this section here, we could actually probably get away with quite a large value of Y plus, because the CFD code is going to correct the wall shear stress for us, and we're probably going to get quite an accurate solution. So our Y plus target, I've put it as a bit larger this time, a value of 40, and we only need 10 layers because the initial cell is already quite thick because we've got a Y plus of 40 now. So 10 layers through the thickness. What I want you to do is just spend a minute or two thinking about what sort of layers you might generate here. What dimensions are you going to use for the length scale? What are your layers going to look like? And then plug those numbers into the calculator and see what your growth ratio is in your first layer. Just going to give you a minute or two to think about that one, and then I'll share the screen again and go through the solution. I can see your questions in the chat. I will answer those, but I want you to have a quick go at this flow problem first. You can see that the difficulty with this is actually quite typical of a real flow problem where, you've got different areas in the domain and they're different sizes. Maybe your Y plus would be different in different places, but the length scale is different. What should you actually do? I'll share the screen again and go through the solution. And this is exactly why I wanted to use this as an example problem, because this is exactly the kind of thing you're going to encounter. Now, there are a number of ways you could do this. And the first thing you might do is you might say, well, what if I divide my domain here into 2 blocks? What if I divide it into 2 bits? And I say, well, in this first section of the domain, my length scale is 10 meters. And based on that, I can plug those numbers into the calculator and I get a growth ratio of 1.1 and a first layer height of 1.4 times 10 to the minus 2. You can see this is in centimeters, so these cells are a lot bigger. But then for the second section, I get a slightly larger growth ratio and my Y naught is a bit bigger. So we might expect that actually this, if we meshed this, then we would either, if we split it into 2 blocks, we'd have one mesh in one place, one mesh in another place. That might be difficult for the CFD code because somehow the mesh generator has to match those layers together, and you might get a sudden shrinking or expanding of the layers. And so you could do it that way. You could define different inflation layer controls on different surfaces, and you can do that. But most often you can just use a pragmatic approach, and you can look at this and say, actually, maybe I'll be a bit conservative and I'll use the Y naught that's lower. I'll use the thinner cell because that's going to give, choose the thinner cell because that's going to give me a lower Y plus, a smaller correction. The CFD code will apply a smaller correction to the wall shear stress, more accurate. The growth ratio is lower. So I can use a conservative approach, and I could just use that all the way round. And again, this calculator is an estimator. As always, this is a first estimate. You could even be even more pragmatic and just say, I'll take a value that's halfway between those. I'll take a growth ratio of 1.13, and I'll take a Y naught maybe of 1.42 e to the minus 2. There are different ways you can do it. But in this case, the values are kind of similar. So it's really up to you. This is up to your engineering judgment. And the fact that you've thought about it is a really good sign, because it means now when you look at your solution, you'll go in and look at Y plus and see, well, how does it vary? If I've used a value Y naught of 1.4 e to the minus 2 everywhere, then probably on this surface, my Y plus will end up being a bit smaller than I wanted. So you have to look at the solution and then update it. The other question, in terms of the stretching factor, yeah, most times a stretching factor of 1.2 is a really, really good first estimate, and I normally go with 1.2. If I don't know what to do, 1.2 is always what I'll go to. If I've got if I really want a slower growth ratio and I'm trying to get a lot of layers, then lower values like 1.05. Yeah, even that can work as well. You may find that if you end up with a really high Reynolds number flow, so if you've got an internal flow system where you've got a really heavy duty pump, which is pushing lots of high velocity fluid around, and the Reynolds number is really high, you end up having to use a really thin cell and then a larger growth ratio. I've seen growth ratios up to 1.3, 1.4 even sometimes. But if you don't know what to do, 1.2 is always a good one to aim for. Let's go on to the next section. So we've talked a bit so far in the workshop about achieving that Y plus that we want by setting the first layer height, and we're also changing the number of layers and the growth ratio so we can fit all the layers just within the boundary layer. But the other thing we want to think about is the final layer transition. And what I've done is just taken a section of the inflation layers here, and as the cells go away from the surface, they get bigger and they expand, they inflate. And when we get to that final layer, that layer is going to have a pyramid or a tetrahedron or a polyhedral cell grown on top of it. And this is where it transitions to the free stream mesh that's far away. And what we want is, you may remember from the end of the last talk, we don't want a massive transition in volume between that cell and the next cell, because again, the CFD code calculates the solution at the centroid. And so if we've got the solution at the centroid of all of the layers, and then we suddenly jump to a really big cell, that ends up with a large spacing in the profile, and we can get an error there. So the other thing we want is we want to try and have a transition between the final layer and the free stream mesh that isn't too large. Maybe a factor of 3, 4, or 5 would be fine, but a factor of 20 is probably too large. If the free stream cell is 20 times bigger than the final layer, then that's going to give us a really large transition in cell size. And so what I've got in the calculator, the other entry that you get as an output is the final layer thickness. And what you can do is compare that final layer thickness to the size of your free stream cells, whether they're tetrahedrals or hex core or polyhedral cells. You can compare this final layer number to the free stream cell size. So here's an example of us doing that. Going back to that aerofoil at the start, we've got a velocity of 5 meters per second. I've got 5 meters per second here. The length scale, the aerofoil is 1.2 meters. The dynamic viscosity is that of air, 0.81 times 10 to the minus 5. The density is 1.225. My target Y plus, again, is 1, and I'm using 20 layers. I'm using a lot of layers. And what you can see, the final layer thickness is 1.12 times 10 to the minus 3. So the final layer is 1 millimeter thick. Final layer is 1 millimeter thick. And in my mesh generator, maybe I've set the target cell size for the rest of the domain to be 1 centimeter. So you can compare these two values. And if we divide one by the other, if I divide this 1 centimeter, the size of my tetrahedrons or my hex core or my polyhedrals, by that final layer thickness, you can see the ratio is 8.9. It's close to 10. So that final layer thickness is going to be getting almost 10 times bigger when we get to the next cell. And so what's that telling us? That's telling us that actually maybe we need to adjust some of the other parameters, and actually we might need to use less layers or a slightly larger growth ratio so that we can get that nice transition at the end of the layers. So here's another example for you. Again, just another 30-second example. We've got the water flowing over the cylinder again with the Y+ target there. And this time, I want you to assume that your free stream cell size is 3 millimeters. So all the way around the layers, we're filled with tetrahedral cells, which are 3 millimeters in their characteristic size. If you fill in the parameters for the calculator and then work out that ratio, what's the ratio of the final layer to the free stream cell size? Just give you a minute or two to do that. Okay, let's fill in the numbers. 1 meter per second, 0.5 meters in diameter, viscosity of water, density of water, Y+ of 1, 15 layers. And our final layer is 7.07 times 10 to the minus 4, so 0.7 millimeters. And the free stream cell size is 3 millimeters. So 3 divided by 0.7 is about 4. That'll be a really nice volume transition there from the final layer out to the free stream cell thickness. And doing this calculation, of course, isn't strictly necessary. You don't have to calculate the final layer transition before you even make your mesh. This is just a good way for you to start, because typically when you generate layers in a mesh generator, whether they be unstructured or structured, the CFD code does, well, the mesh generator takes 5 to 10 minutes often to generate meshes. And you probably want to have a good guess that you're getting some nice layers the first time, because otherwise, if you have to just do it manually a few times, it can take you a lot more time. And so, of course, you can also check it visually as well. You can look and you can see, does your final layer look really thin in comparison to your pyramids and tetrahedrals that are grown from the top of the layers? If that ratio looks massive, then you probably need to go and adjust things. And how do we adjust things? What do we do if that transition is too large? So if we have a situation like the one on the left, where maybe that final layer is 10 or 20 times smaller than the free stream cell size, you'll be able to see that when you generate your mesh, that actually the transition there is massive. What do you do about it? Well, there are two ways you can go about it. The boundary layer thickness is still probably going to be the same size. So that dotted red line that shows where the physical boundary layer is stays the same thickness. So you still want the total spacing held by the layers to fill the same space, but you could either use less layers or use a larger growth ratio. And in this case, you can just see, looking at the pictures, maybe this has got 15, 20 layers with a growth ratio that's maybe 1.05 or 1.1. But in this case on the left, this is quite extreme, but you've only got 1, 2, 3, 4 layers, and that growth ratio is probably about 2. It's massive. But it does get a much better transition to the free stream cell size there. So I hope what you can see just from this workshop and this discussion is that there's definitely a balance. And if you have more layers with a smaller growth ratio, then you're going to get better resolution of that boundary layer velocity profile. If you think of the linear sections along the velocity profile, you're going to get really high resolution there. But then the transition to that free stream mesh are going to end up with a sort of a large discontinuous change at the top there, which isn't going to be very good for accuracy. But on the opposite side, if you have a really good change there, then actually the resolution of your boundary layer velocity profile is going to be really poor. You've only got 4 sort of chunky sections, and that's going to get a really inaccurate result. So there's a balance here, and you want to try and choose something where you get a sensible number of layers, but you want to try and get that nice transition to the free stream mesh as well. And to really illustrate this point, I've got this almost final example for you of the flow over a car. So for the car flow, you've got air coming in at 15 meters per second. The car is 4.5 meters long. You've got the dynamic viscosity and the density of air there, and a free stream cell size of 0.1 meter. So 10 centimeter tetrahedral cells around the car and in the wake. But I've got 2 different strategies for you. Both strategies, we're trying to get that y plus of 1 because we want to have an accurate calculation of the wall shear stress, and definitely towards the trailing edge of the car where we start to get the separated flow coming off the back of the car. Using those wall functions with a large value of y plus is going to be inaccurate. So we want that y plus of 1, but the 2 strategies I've got here, one has 30 layers and the other has 15 layers. And what I want you to do is just fill in those numbers in the calculator and then have a look at that transition to the free stream mesh there and see what it looks like. Once again, I'll give you just a few minutes to work those numbers through and have a go with them in the calculator, and then I'll go through what the solution looks like. And hopefully you'll see that that transition to the free stream cell size is actually different when you use different growth ratio. All right, let's have a look at the solution. Again, filling in the values, quick and easy. And hopefully as well, you can see just how quick and easy it is to fill in these values and quickly get fast numbers for what your layers are going to look like. And you could just quickly ping this up on your desktop or even on your phone if you're meshing, just to give you that first look at how your layers might look before you click mesh on your mesh generator. So let's look at strategy 1, what happens? Well, if we look at strategy 1 with 30 layers, the final layer height is 0.014, so 1.4 centimeters, and that final layer height is 10 centimeters, so 1.4 and 10 centimeters. The ratio of that final layer to the free stream cell size is about 7.1. And if we do the alternative strategy, use 15 layers, you can see that the growth ratio is much larger, a growth ratio of 1.57 compared to a growth ratio of 1.21. But of course, the compromise is there that the final layer height is 0.29, is 3 centimeters, and actually the ratio of that final layer to the volume is only about 3. So this layer height is actually going to be it's going to be really close to that final volume, and you're not going to get any sort of discontinuity in that velocity profile. But In this case, which one would you choose? Hopefully now you can see you've got different strategies and that there's a compromise in there. And definitely in this case, I think a growth ratio of 1.57 is too high. You're not really going to be capturing that velocity profile very well. And the standard recommendations that that were mentioned in the chat and we spoke about earlier, growth ratio of around about 1.2 tend to be good enough for the boundary layer resolution. And in this case, a ratio of 7.1 is probably getting towards too large, but will probably be okay for this scenario. And you could always do things the other way around. You could, of course, reduce the free stream cell size a bit. You could bring that down to 5 centimeters if you wanted to really get a good transition. Or when you get really good at meshing, you may even be able to have some region around the car that maybe has 5 centimeters as the free stream cell size, and then far away you could have 10 centimeters, 20 centimeters. So this is the idea, is that all the time in the CFD mesh, we're trying to get a nice smooth transition in the cell so that that linear velocity profile throughout the domain is well represented. And actually the final thing that I'd put in the talk, I think we spoke about briefly at the end of the lecture. So I'll just go through it, and I don't think we need to calculate this at all. But in some flow scenarios, you may not know what the value of the quantities to put in the calculator are. So if you have natural convection, or if you have a multi-phase flow, for example, you may not know what these parameters are. And particularly with natural convection, the velocity is going to develop in response to the heat being placed into the domain. In this case, we have a hot plate. Maybe the plate is at 100 degrees. We don't know how fast the flow is going to be moving as it's heated by natural convection. And so we don't know what the velocity is. Likewise, if the plate is really hot, the density reduction is going to be much larger, and we also don't know what the dynamic viscosity is. So cases like this might appear intimidating, and you think, oh, I don't know how to mesh this because I don't know what any of the parameters are going to be. And it's important to always bring this back and remember that the layers calculator that you've got here and any hand calculations you do are that first estimate. We're trying to estimate that first value of y plus. We're always going to put in an initial simulation, look at the results, and then go back to our mesh and maybe reduce that first layer height and change the growth ratio and run again. So we're only looking for that first simulation. And what could we do? What could we do for this scenario? Well, actually, what we can do is just use engineering judgment. What do we think the velocity is going to be? What do we think the properties are going to be? And as I mentioned before, you can always just use, particularly for natural convection, unheated values for the density and dynamic viscosity of air, because the change in the Reynolds number actually isn't that large. So here's an example, and I'll just go through it with you. So imagine you've got natural convection in a room. So you've got the room of a house, and there are some heaters or radiators or the ovens on in the house. And so the local temperature of this boundary is set to 50 degrees C. You've got ambient air coming in, 50 degrees C here. What layers am I going to generate on the walls of my room in my house? Well, the first thing I'm going to do is I'm going to look at this and I'm going to say, well, actually the flow that runs along the wall, maybe for my first estimate, I'll go with a y plus of 30, because it's probably reasonably well approximated by that flow in a pipe, although it is heated by natural convection. I may need to reduce y plus later. So I'm going to go for my first estimate, just a y plus of 30, because it's going to be an initial mesh. I'm going to have to update it anyway. 7 layers. I'm not going to use that many layers. So it's going to be a mesh that's nice and small. And dynamic viscosity and density, I'll just use those as the value of ambient cool air, which I know at 20 degrees C. And then for velocity, how fast do I really think the air is going to be moving through a room? And you can think about this, that you only really need to get the order of magnitude right. And if you think of a hot room, the velocity of the air is probably not going to be much more than a meter per second. That air is going to be whipping through the room, probably moderately fast, but you've not got 10 meters per second. and you've not got 1 centimeter per second. So a value of 1 meter per second is just a reasonable estimate from engineering judgment. And you can plug these numbers in. Let's go ahead and do that. Velocity of 1 meter per second. Length scale, my room is 5 meters wide. I've got the dynamic viscosity and density of air, Y plus of 30, and I only want 7 layers. Calculate. And not sure why the values aren't showing up there. I probably typed in something wrong. But the growth ratio is about 1.2. Surprise, surprise, the growth ratio often is around about 1.2. And my first cell height is only about 2 centimeters. So I just wanted to close off with a few closing thoughts for this talk. That sometimes it is difficult to estimate the size of these layers if you have a particularly difficult flow like natural convection or multi-phase flow. But experience shows, and I think we've realized this just through discussion, that if you really don't know and you really don't know what to do with your CFD mesh, often a growth ratio of 1.2 tends to work out absolutely fine for that first guess. And then for the first cell height, you don't even need to use the calculator. If you carried out enough CFD, what often happens is that the first layer height, if you use 0.1 millimeters, that will often get the Y plus around about 1. And if you use a first cell height of a few millimeters, that often gets the Y plus around 30 to 50. These are really good sort of rules of thumb, which when you end up doing a lot of CFD, like someone like me does, you end up sort of knowing off the top of your head, and you can be really lazy if you don't know what to do. This is often a really good first estimate for those CFD meshes. And the most important point I wanted to make in the box at the end is that everything we've done in the workshop and everything I've talked about so far, this is just for that first guess. You're always going to have to look at your CFD solution, and as well as looking at things like the convergence, the residuals, the lift and the drag coefficient and the pressure contours and things, you also need to look at your Y plus. Y plus is an output. Look at it, see how large it is. And you can also, when you plot your profiles normal to the wall, can you see, are they smooth? Are there any discontinuities in the profiles? And then you're always going to have to go back to your mesh and update it anyway. Now I noticed there were 22 layers. Yeah, and I suppose the number of layers I haven't really spoken about as well. How many layers should you typically use? This is, if you look online at various resources and in CFD forums, many people give sort of rule of thumb recommendations for how many layers should you aim for. And if you're aiming for that Y plus of 1, because that first layer ends up being so small, often you do end up having to need to use 20 or 30 layers, you know, that with a massive set of inflation layers around your aerofoil. And so you'll often see recommendations of 20 to 30 layers. But if you are going for that coarser, lower resolution mesh for ducting and pipe flow, and your Y plus is only maybe 50 or 100, often you can get away with 7, 10, 12, 15 layers. That often seems to work out fine for people. So there's a lot of engineering judgment here and a lot of experience, but hopefully I've given you the tools to think about your case and you know how to approach it. And that's really my aim and my hope for this talk. So that's just about everything I wanted to cover. If you guys have any questions, please leave it in the chat or unmute yourself and let me know.
Thanks so much, Aidan. We'll wait a couple of minutes.
Yeah, it's a lot to take in. And I'm going to be doing more discussions and things on meshing in future, because I know it's quite an intimidating topic. And definitely when I first learned, there's hardly any guidance out there at all on how do you go about meshing something? What's a good mesh? How does it look like? Most people say if your Y plus is 1, then your mesh is good. Can you go back to the natural convection example? Yeah, of course. Let me just share again. I probably went over that a bit fast. Yeah, so how did I estimate the velocity? Well, the important thing here is that in the, maybe I can get up the calculators. Here we go. So how the calculators are working is to calculate the layers, we are estimating how thick the boundary layer is, how thick the boundary layer is going to be. And the empirical correlations that the calculators use to make the estimate are always based on the Reynolds number. And of course, Reynolds number, you need the density, the dynamic viscosity, the velocity, and the length scale. But there's a square root dependence here on the Reynolds number. And so actually small variations in the Reynolds number, so if your velocity goes up by 20% or goes up by 50%, it probably doesn't make a massive difference. What you care about is going to be the order of magnitude of the Reynolds number that you're using in the estimate. And so when we're looking at natural convection in a room, this is where you need to think. You need to think critically using engineering judgment. You can always look up, if you really want to know, you can always look up examples on the internet, look at papers, what values of velocity do people typically predict for natural convection. But I just chose to use my own engineering experience and just looked at the temperatures. So I've got an air temperature of maybe 20 degrees coming in from the ambient, and the temperature of the surface is only 50 degrees. It's warm, but it's not very hot. If you think the oven in your house probably goes up to 200 degrees, which is very hot. And if you ever open the oven door, the air always comes out pretty fast. So with a surface temperature of only 50 degrees, I don't imagine that the air is going to be coming in through the room too fast. And based on my own experience, 10 meters per second, if you think about how large 10 meters is, 10 meters is large. Is the air going to be whipping across 10 meters in 1 second? Probably not. That's too fast. But is the air going to be moving 1 centimeter every second? Probably not. It's probably going to be a bit faster than that. And so I just taken an arbitrary value in between of 1 meter per second, with a meter being probably about that long. Yeah, it's moving about that fast every second. That was the engineering judgment I used. It's very, very rough, but you can always do these things when you're just making a first approximation for things. Yeah. So the question from the chat is a good workflow for prism layers is: 1, estimate the boundary layer thickness from the Reynolds number. Yes. Then assume the prism layer thickness is equal to the boundary layer thickness. Yep. Then use the tool or write the equations yourself to find the number of layers and the growth ratio to get the prism layers to fill the boundary layer. Yeah, that's a really good way to proceed. Some other caveats in there as well is that the Reynolds number, using that to estimate the boundary layer thickness, you're also using the Reynolds number to estimate the friction velocity and the Y plus value as well. And that's also here in the guide as well. You can see higher up, the Reynolds number, we use that to estimate the skin friction coefficient, which gives us the wall shear stress, the friction velocity, and the first layer height. So the Reynolds number is doing 2 things, telling us the boundary layer thickness and that first layer height as well. Maybe while we're on that topic as well, another question which I've had in the past from people as well is, this is all fine for an external flow. If I've got flow over an aerofoil and I'm working out the boundary layer thickness as that develops. But what happens if we have an internal flow? So we have flow in a ducting system, in a piping system, in a water pumping network, for example, and the water is going along the pipe. Obviously, as the flow comes into the internal flow system, we get the initial boundary layer development when we come in from the inlet, but eventually the boundary layer fills the whole channel. When we have an internal flow, the boundary layer fills the whole channel. And so what would we do with this calculation? Because the boundary layer thickness isn't really important for us anymore. Well, what you can do is, rather than saying, I want the prism layers to match the boundary layer thickness, you can say, I want the prism layers to fill a certain fraction of the pipe diameter. So maybe I could say, if I've got a turbulent flow and I know the velocity profile is going to have a power law, maybe I want the layers to fill 20% of the pipe diameter. So I've got inflation layers on the really important bits at the top and bottom of the pipe. I want it to be 20%. Then you could do the same calculation, and you'll see in here, there's a line where we equate the total thickness of the layers to the boundary layer thickness. Instead, you could equate the total thickness of the layers to, say, 20% of the pipe diameter, and then follow through the same calculations, and you can do it that way as well. So that's how you would modify the calculation procedure for an internal flow. I'd forgotten to put that in the slides, but hopefully that makes sense to people, and if they've got an internal flow, they can use that.
Cool. And I'll also, shameless plug, I'll put the link to your courses on Udemy in the chat as well.
Oh, that's fantastic.
Should people check out anything else, Aidan, or do you only have courses on Udemy?
So at the moment, I've got on Udemy, I have a few courses which show the basic fundamentals for how a finite volume CFD code works. And fundamentals 1 goes through basic convection and diffusion and how that's solved for a mesh in 1D. Fundamentals 2 is quite interesting, actually, because I show the next stage, which is actually how does the CFD code modify that wall adjacent cell depending on Y+. That's actually in there. And so if you want to go further and you want to know, well, I've given it a value of Y+, what's the CFD code actually doing? How is it modifying the wall shear stress and the wall heat flux? That's in fundamentals 2, so you can check that one out there. And as always, if you guys haven't found my YouTube channel yet, check out Fluid Mechanics 101 on YouTube. I've got loads and loads of detailed information on all aspects of CFD there as well. And I'll have plenty more to come in future, plenty more on meshing as well. So if you're struggling with meshing, I'm going to have plenty more coming next year on that one.
Really cool. All right. And if there are no more questions, I think we can wrap it up. Then Aidan, I'll send you an invite maybe for later.
Fantastic.
We'll have a quick chat.
And for those of you guys listening as well, just wanted to say I do really appreciate you coming along and joining in on the courses. This is the first one that I've done as well, so I am really looking for feedback. If you found it useful, if there were things that you like, please let Joseph know or myself know either by email or message, whatever format you want. Please let us know. And if you have other things that you think could be improved, or you'd like further information, you think, oh, this would be really good if you covered that as well, also let us know, because I'd really like to improve this in future so you guys can get even more from it.
Sounds good. To all the guys attending, maybe after the session, once the session closes, you have an email where you can rate the course, maybe with a small comment. So please do that, and I'll forward it to Aidan. That would be really, really great.
Yeah, fantastic. Thanks, everyone.
Awesome. And thank you so much for your time.
Cheers. And I'll see you all later. Thanks all.
Yep. Bye-bye.